Alright, pause this video anytime you need to. Take out a piece of paper. We're going to do some Lewis structures. I showed you this last Thursday. At the bottom of your notes, it had the fast way to make Lewis structures for covalent bonding, molecules that do covalent bonding, and that had these rules here, or sorry, guidelines. So take those out, and we're going to do some problems. I'm going to do some problems for you, and I showed you one of these already. So the first one we're going to do is water. So on your paper, write down H2O, and then we're going to first come up with a number of valence electrons. So there are two hydrogens, valence electrons. There are, here, I'll start over. Valence electrons is equal to 2 hydrogens, 1 oxygen. We've got each hydrogen is in group 1, so 1 valence electron. Each oxygen is in group 6, so 6 valence electrons makes a total of 8. That's step 1. Step 2, arrange the atoms in a skeleton structure, connecting them with single bonds. Usually the least electronegative one goes in the middle, but hydrogen can't go in the middle, so we'll put oxygen in the middle, single bonds, called a skeleton structure. That's step 2. Step 3, complete octets of the outside guys, but hydrogen doesn't want 8, it only wants 2, so we're not going to put any more electrons around the hydrogen, it's already happy. Step 3, if all the valence electrons have not been used, put more on the central atom, or put any left over on the central atom. We've used, remember bond is 2 electrons, so 2, 4. So we've used 4, we have 8, we've got 4 more we can put onto the central atom. Now we've used 8 valence electrons. If this guy were not happy in the middle, we would steal from somebody and double bond or triple bond if we have to, but it's already happy. So there we have it. We're done with water. That's the Lewis structure for water. Now we are going to do a polyatomic ion. We'll do the sulfate polyatomic ion. If you remember what polyatomic ions are, they are many atom ions, right? Polyatomic ions. Many atom ions. And they're held together, so some atom is stuck to some other atoms with covalent bonds. Okay? So something like sugar uses covalent bonds, but in this case we don't have a molecule, we have this whole thing that's stuck together by covalent bonds as some kind of charge, like 2 minus or 3 minus or something like that. So it's a many atom ion. The atoms are held together as a covalent, by covalent bonds, but together they've gained or lost electrons as a whole thing. And this usually, there's only one positive polyatomic ion, ammonium, so usually they gained electrons from somewhere else, so there would be something else like, some other positively charged thing nearby, or, 2 of them, or a 2 plus, to make an ionic compound. But the ionic compound has a polyatomic ion that's held together by covalent bonds, and we're going to draw the Lewis structure for some polyatomic ions. So we're going to do the sulfate polyatomic ion, SO4 2 minus. So you can write that down on your paper. First thing we do is find the number of valence electrons. 1 sulfur, 4 oxygens. Sulfur's in group 6, so is oxygen, it's in group 6. And then we have to add or subtract something here. If it's a minus, has it gained or lost electrons? If it's a minus, it's gained electrons, and it's gained 2, so we're going to add 2. Remember, for us, we always have to have an even number of valence electrons to get everybody happy anyway. So if you ever get odd, you did something wrong, because we're not going to do any of those. So 6 plus 24 is 30, plus 2 is 32. That's step 1. Find the number of valence electrons. Step 2, arrange them in a skeleton structure. Sulfur is less electronegative than oxygen, it's below it. And if you ever end up with one of something and a lot of the other ones, it's pretty much always this one's the one in the middle. So we're going to get the sulfur in the middle, and we're going to put the oxygens around. And when we do things for now, we'll do maybe a couple later that are different, but we're always going to have one central atom, one thing, and everything else is around it in the circle. Okay? So that's step 2. Step 3, complete octets of the terminal atoms, the outer atoms. Oxygen does want 8, so we're going to give everybody on the outside 8. When we're done with that, we're going to count up how many we've used to see if we have any extra, come on, to put anywhere. Alright? So, remember I told you if there is a central atom, the easiest thing to do is just cover up the middle one and start counting. So if you ignore the sulfur, this has 8, right? We made it happy with 8, so 8, 8, 8, and 8. 4 8s is 32. Where we do not have any extra valence electrons. So we can't put any more on the sulfur. Step 5. If the middle guy, the central atom, does not already have an octet, we'll steal from somebody to make double bonds, but the sulfur does have an octet already. 2, 4, 6, 8. So the sulfur is happy. So according to your rules, we're done. But if you remember, when we have ions, what we do is we put brackets around the ions. So this whole thing, all of this thing, all stuck together with covalent bonds, is an ion with a 2- charge. So we're going to do that. Okay, there we go. Okay, so we're done with that one. If you Google this, it gets more advanced than this. People will talk about how this isn't quite true, and they'll start talking about formal charge. We're not going to do anything with formal charge. We're not going to explain what they're talking about if you watch a video that has to do with formal charge. We're going to end here. Everybody's happy? We're happy. Okay? Let's try number 3, a third one. The nitrite polyatomic ion. That's NO2 with a minus charge. Not a 2- charge, right? It's just the minuses up there. So, first thing we do is count the number of valence electrons. Valence electrons, 1 nitrogen and 2 oxygen. And nitrogen is group 5. Oxygen is in group 6. If you were to count those up right now, we actually have 17. We can't have an odd number, so you got to look right there. Is it gained or lost an electron? A minus means it's gained 1. We're pretty much always adding 1. The only time you would ever subtract 1 is when you have ammonium. So 5 plus 12 is 17, plus 1 is 18. That's step 1. Step 2, put the least, usually the least electronegative atom goes in the middle. Nitrogen's less electronegative than oxygen. It's going to go in the middle. Okay, so that is step 2. Step 3, make the outside guys, the terminal atoms, happy with octets, unless it's hydrogen. And this is not hydrogen. The oxygens want 8, so we already have 2. I'm sorry, man. We already have 2 there, so we've got 2, 4, 6, 8. Sorry about the camera work here. Doesn't like it. Okay, we'll do the other side of oxygens. And then, if you cover up the central atom, man, come on, camera, focus. There we go. This and this, if you cover up the central atom, there's 8, and 8 makes 16. Have we used up all of our valence electrons? No, we have 18. So we're going to put 2 more right there. That is step 4. If not all valence electrons have been used, place any extra electrons on the central atom. Step 5. If the central atom does not have an octet, use lone pairs from terminal atoms to form multiple bonds. So, is the nitrogen happy? It is not. It only has 6. So we're going to steal from somewhere. I usually use pencil to do this, but what people will do sometimes is just kind of go and take away some of those. And we're going to make a double bond there. So I'm just going to rewrite it here. And then it has a charge, so the whole thing gets brackets and that -1 charge. You could have also stolen from this one. You could have a single bond there and a double bond there. Okay, this is a good one because you have to do all 5 steps on this one. So it's a really key. If you missed this, go back and watch it again. Because this is a good one to show all of the different 5 steps. And lastly, let's end with a little bit of an easier one. We'll do the ammonium polyatomic ion. Remember, it's the only one that has a positive charge. So we'll do valence electrons, 1 nitrogen, 4 hydrogens, and nitrogen group 5, hydrogen group 1. And then this is the one time where we're going to subtract 1. It's a plus, so it's lost an electron. So 9 minus 1 is 8. That's step 1. Step 2, you put the less electronegative one in the middle, but never hydrogen in the middle, because it only wants to form one bond. So nitrogen's got to be the one in the middle. And we're going to put them all around the central atom, but single bonds. This is called the skeleton structure. Like, I guess like the sticks are like the bones, the bare bones, just single bonds. That's step 2. Step 3, complete octets of the outside guys, but the hydrogens don't want anything more. Alright, so they're done. That's step 3. Do we have any extra valence electrons? We've used 2, 4, 6, 8, and we had 8, so we don't have any to put anywhere else on that nitrogen particularly. And then step 5, is the middle guy happy? The answer is yes, so we're done. And then, I guess we're not done it completely. We're done with those guidelines. We box it up and put the charge or brackets on it, and put the charge on it, plus. Okay, there is one other thing I will talk about here. At the end of the guidelines, it says, if the central atom does not have an octet, use lone pairs from terminal atoms to form multiple bonds. But it says, in the second period, only carbon, nitrogen, and oxygen form multiple bonds. This leads to an exception in the octet rule when atoms like beryllium is combined with either hydrogen or halogens, like group 7 guys, as in BeH2, beryllium hydride. Since beryllium does not form multiple bonds, the central atom is electron deficient. Deficient means it doesn't have enough. So the paper I gave you to solve today to work on today doesn't have any of those, but if you ever get something, beryllium you would have thought would make an ionic compound anyway with, BeCl2 or something like that. You say BeH2. Isn't that ionic anyway? Well, turns out beryllium's electronegativity is high enough it doesn't lose it completely. So, but beryllium, boron, and we said carbon, nitrogen, and oxygen, those can make double bonds. They're fine with it. Fluorine only wants really one bond. Anyway, neon doesn't really make compounds at all, so we're really talking about like boron and beryllium. Those are the ones you'll see where you'll get something that looks something like this. You'll end up with boron, and it will end up having 3 bonds. You're like, but it's not happy. You're right. And you might want to steal and double bond, but boron can't double bond. Same thing with beryllium. You'll end up with something like this. And you say, the beryllium isn't happy. It only has 4. You're right. But it just can't double bond, so it's stuck like that. Okay? We'll see some examples like that later, but your paper for tonight doesn't have any of those. So start working on these. We did water together. We're not going to worry about shapes. Okay? Don't worry about that. We'll fill that in later when we learn how to do shapes. We're just going to do Lewis structure. So start by counting the valence electrons. Put it together a skeleton structure with single bonds. Make the outside guys happy. Count up the valence electrons. Put any extras on the middle guy. And then make the middle guy happy if it's not already happy with double or triple bonds. Have a great day.